Steinhauer here. Welcome back. We have been talking about stellar remnants, the things that are left behind after stars die. And when massive stars die, sometimes they leave behind neutron stars, and we've been talking about those neutron stars are. So let's talk more about neutron stars and how we can observe them and what they look like in real life. But first, just some visual representation of the size of a neutron star. Again, it's hard to wrap your brain around a lot of these things. Certainly the densities and the masses involved, but the sizes of these things are now actually starting to come into our everyday reality, right? So we said that a neutron star has a typical diameter of about 10 kilometers. This is what a 10 kilometers diameter circle looks like centered on the village of Geneseo, right? It doesn't even stretch to Canisius Lake on the one side. So this is a fairly small, like you could run, if you were in really good shape, you could run the diameter of this. You could run a circle around a white dwarf, theoretically, if you could stand on it and not get squished, but you could not. Moving up to Rochester, it's about the size of the city of Rochester, right? That is another 10 kilometer diameter circle. You can see if we center that on the city of Rochester, it does not even reach up to the lake. It does not even reach to Oronokoi Bay. It does not even reach to down here at the bottom, Henrietta and the malls and things down here. So this is, when we say about the size of a city, we're talking about a city like Rochester. And so that is a neutron star. You've taken something that's more massive than the sun and compressed it down into something that's about the same size as Rochester. That is a neutron star. That's what we're talking about. Interesting factoids about the discovery of neutron star. This is actually an interesting story. There was a graduate student in 1967 by the name of Jocelyn Bell who set up an experiment to look for fast changes in radio pulses. This is something that's really hard to do in astronomy. You normally, when you're looking at something faint, either in the radio or in the visible, you have to integrate for a long time, right? So let's say you have something faint and you might integrate for a whole minute, right? So all of the light that you receive from that minute, you get binned up into a single data point. You don't know, and then you can take another data point the next minute and another data point the next minute. And that may not be changing, but you may not know if there's changes that are happening more rapidly than that. Like if this thing is turning on and off once a second, you won't know that if you're integrating over a minute. And Jocelyn Bell devised a way to test whether or not some of the radio sources that they were looking at that they didn't understand varied on smaller time scales. And she found that some of them do vary on very short time scales. This is a diagram showing the brightness of one of these radio sources as a function of time. And you can see the x-axis here, you're talking about seconds. Over the course of 20 seconds, this object gets brighter and then fainter and then brighter and then fainter multiple times. There are peaks after peak after peak. This thing seems to be blinking. It seems to be turning on and off. It seems to be bright 1 second and then dim the next second and then bright the next second for a short period of time and then dim the next second. It's blinking on and off. These things are known as pulsars. Not because they're physically pulsating, but because we get pulses of light from them every so often. Now, the tragedy of this story is that the Nobel Prize was awarded for this discovery the next year, and it was given not to Jocelyn Bell, but to her PhD advisor. And her PhD advisor accepted the Nobel Prize and didn't even mention Jocelyn Bell in his acceptance speech. And so this is one of the tragedies of the Nobel Prize process, is that sometimes they get it wrong. And who deserved that Nobel Prize? It was actually Jocelyn Bell. So that is one of the sad stories of the Nobel Prize process. But she's still a famous astronomer today. She shows up to meetings, and she should have a Nobel Prize for this discovery. We've discovered now lots of these things. Here is one at the center of the Crab Nebula. The Crab Nebula is a supernova remnant of a supernova that the Chinese Chinese astronomers observed in the year 1054. And this is what it looks like today. At the center of the Crab Nebula, though, where we would expect a neutron star to be, we see a pulsar. And this pulsar isn't blinking on and off once a second. It's blinking on and off 30 times a second, right? Every 0.33 seconds, you get a strong blink from this thing. And in between each of those strong blinks, you get a weak blink, interestingly. So the whole process from strong blink to weak blink to strong blink takes about 0.033 seconds, or 30 times per second. This thing is blinking on and off. That's remarkably fast. Things in astronomy don't usually change that much and that fast. Why? Because big things take a long time to change physically, just because of how large they are. You need something that's very small to be able to change this fast. And that's why we think, that's what we think, one of the reasons we think pulsars are neutron stars is they change so fast. Here is some more examples of the Crab Nebula pulsar. If you zoom in and look at it in visible light on the right and X-rays on the left, what this object looks like. And you can see some characteristic telltale signs of some interesting things going on, right? You see a disk of material surrounding a very hot, dense object, right? And this disk of material is probably physically accreting onto the surface of the neutron star, right? What does accretion mean? It means that material is falling onto the surface. And interestingly, if you have a system where you're dumping material onto something that's presumably spinning pretty fast, you almost always get these jets of material that go out from either pole of that object. And so we see this both in the X-rays and in the visible light, this disk of material and the jet of material that's coming out in either direction. And that's important in understanding what these things actually are, because two properties of a star go way up when you make a neutron star. This is actually not true. Thousands of properties go up in making a neutron star, density and things like that. But I'm thinking particularly of two of them that are important for making a pulsar that we're talking about right now. And those two properties that I'm thinking of are the spin rate, how fast that neutron star is spinning. Why does this happen? It's called conservation of angular momentum. When you take an object that's spinning slowly and you make it smaller, that object must spin faster. This is how ice skaters work. You might notice when an ice skater spins on the ice and she has her arms out to the side, she's spinning slowly. All she has to do is pull her arms in and she will start spinning faster. This is conservation of angular momentum, except that you're taking something that's really massive in the size of the Earth, like a neutron star, and collapsing it down into the size of something that's a city. That's a phenomenal many order of magnitude change in size. You get a many order of magnitude change in how fast this thing is spinning. The other thing that goes way up when you make a neutron star is the magnetic fields. So the strength of the magnetic field that is controlling this object has to go way up when you make a neutron star. And so basically stars are like giant bar magnets, and when you make them really small, you drag those field lines down to the center and you make them stronger. You pull them closer together and you make them stronger. And so what happens when you have a star with a strong magnetic field? Let me just draw a quick diagram of what a neutron star looks like. There's a neutron star. Let me draw some field lines now. This is like a bar magnet. It has a north pole and a south pole. If I were to draw magnetic field lines, they might look like this. Out one side and then out the other side, ish like that, right? And so what happens when you have, usually there's a disk of material around that for view from the side might look something like this. The charged particles that are in, because they're so hot next to this neutron star, can't actually fall right onto the surface of the neutron star itself. And so they get caught up along these field lines, right? And they get channeled, they don't want to cross these field lines because they're so strong. They get channeled up along them and they get funneled into the two poles of the neutron star itself, right? And some of that material presumably does reach the surface of the neutron star, but some of it gets caught up in this magnetic field, and you get a jet of material that comes out of both ends of this neutron star. So the details of how that happened are complicated, and we don't really understand it, but that's what we think is happening. We have a jet of material, and that material will sort of spiral along the magnetic field lines that are there and emit radiation also in this direction and this direction. Okay, so that's cool, and you get this jet of material. How does that give you a pulsar? Well, what if the magnetic axis and the rotation axis are not perfectly aligned? This jet happens along the magnetic axis because that's how these materials are being funneled in. But what if the rotational axis looks like something like this? What if the star is spinning along this axis in a particular direction? Well, what's going to happen to this jet of material? Well, it's going to be pointing in this, well, it's going to be pointing in this direction at this point in time. But as this whole star spins, the direction of that jet is going to change. And in fact, it is also going to spin around in a big circle like this. So at another time, it's going to be pointing in this direction, and sometimes pointing in this direction and this direction. Wherever it happens to be as that star spins around is where that jet is going to be pointed at. And that's what we think is happening in neutron stars. Here is a still from an animation that shows this effect. Let me see if I can get the animation on itself. And here is the animation itself. Here is a showing you how this works, right? You can see the neutron star at the center in red. You can see the white lines that indicate where the magnetic field lines are, and the green things are the jets that are coming out of the north and south poles, magnetic poles of this star. But you can see the rotation axis and the magnetic axis are not perfectly aligned, just like they're not perfectly aligned on the Earth. And so you have these jets of material that are swinging through space. And if we happen to be in the upper right-hand part of the diagram, we're going to get a pulse of light every time this beam sweeps by us. It's almost exactly analogous to a lighthouse, right? This is how a lighthouse works. You have a beam of light that swings around, and if you're just looking at the lighthouse, you just get a pulse of light from this lighthouse every time that beam of light sweeps around and passes you in space. Here is another cartoon version of how this looks. You've got, again, a better version of what I just drew. You've got all these magnetic field lines in here. You've got the beamed radiation going into space, and you've got this whole thing rotating around fairly rapidly, and this beam then therefore also rotates around and shines in different directions as the whole star rotates on its axis. Here is another diagram showing how this is kind of like a lighthouse. This is sometimes called the lighthouse effect. We get beamed radiation, and as that beam sweeps through space, we get pulses of light from that particular object. Again, I want to emphasize that pulsars are not physically pulsating stars. There are stars that physically pulsate. Pulsars are not them. They're kind of misnamed, but we do get pulses of light from them. And so that's why they're called pulsars. Okay, so why must, I'm saying pulsars must be neutron stars. There's nothing else that they can be, especially the ones that are spinning really fast. Let's think about why that has to be the case. There are pulsars. We saw the Crab Nebula pulsar spins 30 times a second. There are pulsars that spin 1,000 times per second. Nothing else but a neutron star can physically spin that fast. Why is that? Well, let's think about the circumference of a neutron star. The circumference of a neutron star is just the area around the equator. It's just a circle that has the radius of our neutron star. And I'm even being a little bit generous here, giving a 10-kilometer radius. 2 pi times 10 kilometers, 2 pi is about 6. Our radius is 10 kilometers. We get to 60 kilometers is the circumference of a neutron star, right? the fastest pulsars spin at 1,000 times per second. And we know this because we get 1,000 pulses from them a second. And so the velocity, what is the velocity of a neutron or a particle on the equator of this object, right? It has to be moving in a circumference of 60 kilometers 1,000 times per second. And so the velocity of that object, that particle on the surface, must be 60,000 kilometers per second. That is 20% the speed of light, right? It is about the escape velocity of a neutron star. And so any faster, and this thing would physically spin itself apart, despite how enormously large the gravitational force is on the surface of this object. Anything larger than a neutron star would be torn to pieces immediately if it tried to spin this fast. And so at the very least, the rapidly rotating things must be neutron stars, and we have no reason to believe all the other ones are not neutron stars as well. Okay, so that's cool. Neutron stars and pulsars are interesting astronomical objects. But there's even more interesting astronomical objects out there, right? What about very massive stars? What if you have your supernova collapse and the thing that you're making is the neutron star that you would have at the center is more than 3 solar masses? It turns out that there's a Chandrasekhar mass limit for neutrons as well. Remember, the Chandrasekhar mass limit is the size limit, the mass limit for how big you can make something supported by electron degeneracies, which is an upper limit on the size and the mass of a white dwarf. There's something similar that sets the upper limit on the mass of a neutron star, and it's about 3 solar masses. If the remnant that you make is greater than 3 solar masses, you can no longer support the object by neutron degeneracy pressure either. And therefore, something must happen. The thing must collapse again. And at this point, we know of no force that can support the star. And so you're going to be collapsing down into basically nothing. And these are very interesting objects. And we will spend the entire next class talking about these very interesting objects. Stay tuned and hope to see you then.